thank you very much for joining us. This is something completely new, as you've probably worked out with everything that's gone on. So this is a lecture that we usually deliver in public libraries. So we thought we'd adapt it to the current situation and try and work it out for, the online setting. So my name is Luca. I'm a staff member at CU Adelaide. We're one of the head office for Children's University Australasia. And I probably should preface by saying I don't actually have any qualifications in space science or anything. This is just a bit of a passion project for mine. So we'll be doing my best to share some knowledge that I've kind of picked up just from my own sort of interests. Happy to have some questions throughout the session. There is another one of my staff members who's going to be going through the comments. So if one of you in the audience do have a question, feel free to send that through. And at the end of the lecture, they're going to send those through to me, and we'll be able to read those. So hopefully I can answer some of them for you as well. Now, this itself will be worth 1 hour in your Children's University Passport to Learning, and there's a bit of an activity throughout that will be your demonstration of that. But there will also be some extension activities to follow up, and they will be on the CUA portal or available for download via the CUA website. So there are some extra ways to get some hours throughout as well. So just to get things started, we want to talk about what we would consider our place in space, or our cosmic address. So we know that an address, it's fairly straightforward. When we want to send a letter or something, we write the address down, we put it in the post, and it finds its way there. And we're all very, across that in terms of how it works in the world. But how would it work if we're going through the universe? Because if we were trying to send a letter to another planet or another galaxy, we need to know the address. So I just want to start off by talking about that. From a cosmic point of view, in terms of our cosmic address, we start off with the planet Earth. Okay, from a cosmic point of view, a planet is basically, probably could go moon as well. We're not on a moon, so we won't worry about that. But Earth is the first line of that address. That's basically like let's say your street number. After that, we move up to our next layer of the address, next line of the address, where you might be putting down, say, your actual street name. For us, that is our solar system. So our solar system is a group of planets that orbit a star. And we call ours the solar system because it's the one that Earth is found in. So that's your next line of your cosmic address. Beyond that, things start to go on such a large scale that it can be quite hard to comprehend. But the next layer of our cosmic address is the Orion Arm. Now, the Orion Arm is a small part of our wider galaxy. So if you want to consider where that might fit in, the Orion Arm might be, for example, a suburb within your larger city. Okay, so if Earth's your number, solar system is your street name, Orion Arm might be your suburb. So the Orion Arm is a part of the galaxy with which we find Earth in. As we get even larger, we look to the name of our galaxy, which is the Milky Way galaxy. Now, our galaxy is a system of stars, of gas and space dust that are all bound together by gravity. Gravity is going to be a common thing you hear about throughout this lecture, and it's responsible for a lot of the phenomenon we see throughout the universe. So gravity is a really important one, and one of the things it does is it binds these galaxies together. Now, galaxies can be absolutely massive. We're looking at somewhere between 100 to 400 billion stars in our galaxy alone, and ours is by no means the biggest galaxy. It is, of course, called the Milky Way. So we've got Earth in the solar system, located in Orion Arm in the Milky Way. Now, beyond that, we then have what we call our local group. Now, the local group are two galaxies, or the two closest galaxies to us. That is the Milky Way and also another galaxy that we call Andromeda. Now, there are some smaller galaxies around it, but we talk about the local group being predominantly the Milky Way and the Andromeda galaxy. Now, these galaxies are, once again, absolutely massive in terms of number of stars, but then we also want to group our galaxies together, and that's where we get into something called, the local group, my mistake, is the two galaxies, the Milky Way and the Andromeda, and then we move into the Virgo supercluster. So that's an even larger group of galaxies. Now, there are approximately 10 million of these superclusters throughout the universe. And these, once again, a Virgo supercluster or any supercluster after that is a group of galaxies themselves who are bound together by gravity once again. The final line of our cosmic address is what's called the observable universe. And the term observable, you may think, well, that's what we can actually see, or that's what scientists can see, and that isn't actually the case. The edge of the universe is not actually visible. What scientists have determined the universe to be, or the observable universe to be, is the distance that light could have traveled since the inception or since the birth of our universe. So it's predicted the universe is about 13.8 billion years old. So the width of the observable universe is the distance that light could have traveled within 13.8 billion years. So we move along then, and we go along to what we want to get into these, some more of these in a bit more of a specific manner. So I want to start talking about the universe itself. Now, the universe is important because it is absolutely everything. Like I said, it's everything that scientists know about, everything that we've ever studied, everything that's ever occurred is happening within our universe. It's also so big that we can't even really understand how big it is. Our minds don't really comprehend the actual size of the universe. So, if I were to say to you, let's think about how big your classroom is, you would be able to think to yourself and say, well, yeah, I can estimate how big it is. And if I said, okay, think about how big your playground at school is, you would be able to estimate that as well, because your mind is able to comprehend spaces that it's been in and spaces it's been able to observe. It's very hard for us to comprehend how big our state is. I mean, we know the shape of it and we know where it falls on a globe or on a map, but we can't really comprehend just how big our state, our country, or even our planet is. So that then gets really hard to do when we talk about the entire universe, because it's absolutely massive and we just can't get our heads around it. It's also incredibly old. So like I said before on the last slide, the universe is about 13.8 billion years old. So far older than anyone can really comprehend. And what it does by being so old, it makes it really hard to understand, well, what happened 13.9 billion years ago? What was there before the universe actually existed? And this is a really, really big and important area of science, because scientists are looking for, well, what happened? What initiated the universe? What initiated everything as we know it? Or what was there beforehand? And the most commonly accepted theory is the Big Bang theory. Now, it's still called a theory because scientists, no one was there to see it. There's no photos of it happening or anything like that. So it's always going to be a theory. But in science, when we call something a theory, it's because there's lots and lots of evidence to back it up. And the key bit of evidence that supports the Big Bang is the existence of energy. So I'm just going to go to the next slide and you can see a little bit what I mean. This is a photograph of our universe taken with a microwave calendar. So what I would like you to all think about is, if an explosion took place and immediately after that explosion took place, you could go and put your hand exactly where that explosion took place, have a think, what do you think you would be able to feel? So you're perfectly safe, the explosion has taken place, it's finished, you've gone and put your hand exactly where something just blew up. What do you think you might feel? Now, an explosion is just a very rapid release of energy. So if you were to put your hand there immediately afterwards, you would feel heat, because an explosion would leave heat behind it. Now, the larger the explosion was, the further that heat would spread. You wouldn't need to put your hand right where the explosion took place. You could be nearby the explosion and you would still feel that heat. Now, what you can see in front of you on your screen is a photo of the universe taken through a microwave camera, and microwaves are able to detect very, very low amounts of heat. The universe is still incredibly cold, but the microwave camera is so specific, it can pick up very, very tiny bits of heat, and that's what you can see in front of you. No matter where microwave cameras take photos throughout the universe, there is always evidence of heat. Sometimes there's more or less. I mean, you can see there in the pictures, some bits are red, indicating they're warmer, and yellow, that might be warmer in the blue areas, but there is always heat. And that was the evidence that scientists took to say, well, if there's energy all throughout our universe, the only way that could be there was from one explosion, from a central point that rapidly released all this energy throughout that universe. So now there is one of the activities in the extensions gives you an opportunity to replicate the Big Bang as well. It is a bit messy, so in advance, I'm going to apologize to the parents who I'm sure will be involved in the inevitable cleanup. So moving along now, we talk about our galaxies. There are millions and millions and millions of galaxies throughout our observable universe. We talked before, we mentioned the name of Earth's galaxy. Are you able to remember the name of Earth's galaxy? Hopefully you've come back, you said, yep, it's the Milky Way galaxy, and that, remember, was located in the local group next to the Andromeda galaxy. Now, galaxies are groups of millions and millions of stars which are held together by gravity. Now, like I said before, gravity is a very common theme throughout what we talk about today and throughout space, because it explains why lots of things happen. You know of gravity. You know that gravity is that force that pulls you back to the ground. Every time you jump up, you are fighting against gravity. And every time you land back down, you are effectively losing that fight against gravity as gravity pulls you back down. But it's more than just Earth keeping you on Earth. Gravity is actually a force that takes place between every object. So right now, you'd be looking at a screen, either on a laptop or on a phone. Right now, your laptop has its own gravitational force, and that gravitational force is pulling you towards a laptop, and you, as a body, as a mass, are trying to pull the laptop towards you as well. So right now, you and your laptop, you want to be bunched together. The reason you're not doing that is because your gravitational pull is actually very, very small. You're just not big enough, and neither is your laptop or your phone. And in our environment, there's only really one gravitational force that we can feel, and that is the one that comes from the planet Earth. In your environment, the planet Earth is by far the most massive thing that has an impact on you. And so that is why you don't notice any other gravitational pulls. So if gravity wants to pull everything and bunch it all together, why then don't all of our stars within a galaxy, why don't they all bundle together in one big ball? They all want to get together. They're all really big. They've got their own strong gravitational pulls. Why don't they all just bunch together? The reason we see these stars all spread out is because there are so many different forces, very, very strong forces acting. I'd like you to think about a game of tug of war. You've got two teams at each end. You've got a little, let's say a little string in the middle or a ribbon in the middle that you're trying to move over each half. In a game of tug of war, if one team has a stronger force, they pull that bit of ribbon over the line and they win the game. But think about what happens if both teams are pulling on each end of the rope with equal forces. What happens to that ribbon in the middle? It stays still. If the forces were perfectly balanced, that bit in the middle, that ribbon, would stay still. And that's effectively what is happening throughout galaxies. But there's not just two forces pulling in equal directions. There's millions of different forces all pulling in all different directions, but trying to pull things closer to it. And what happens is, because there's so many different forces, eventually that entire environment within the galaxy finds a point where everything is just balanced. All the forces acting on one another, they're all balanced, so everything just freezes in place the same way that ribbon does in the game of tug of war. So that's why you don't see all the stars and galaxies all bunched together, because all the forces, while they're trying to get them together, they're actually doing a really good job of pulling them all apart as well. And that's why we don't see a big bunch. Taking another step down now, we look at solar systems. Now, a solar system is a group of planets which orbits around a star or a sun as we know it. Now, there may be millions and millions of other solar systems throughout the universe. There is no reason that any star, being so as big as it is, couldn't have its own solar system around it. But we're going to focus just on our solar system for now. Now, our solar system contains 8 planets and over 100 moons. And each of those planets within the solar system, they orbit the sun. But how long that takes them to orbit the sun depends on its distance. And we're going to talk a little bit about the distance because it's really, really important. Now, the first thing I'd like to do, though, is just show you a picture of our solar system. As you can see, we have the sun on the left-hand side. Then you have our 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But have a look at that picture. What do you think is wrong with the image? What's wrong with this image is that all the planets are virtually evenly spaced apart. They're not a scale distance, or the distance between them is not to scale. There are, in fact, absolutely massive gaps between different planets within our solar system. They aren't all evenly spaced. And because we see such big gaps, and because planets like Neptune are just so much further away from the sun, their orbit takes a lot longer. Now, that's still quite hard to visualize. So what we're going to do for the remainder of the lecture is you're actually going to be able to create your own diagram, and which is going to be a scale diagram of the solar system itself. So if you haven't already, please do take a second to go and grab for yourself a ruler, a 30-centimeter ruler, an A4 piece of paper, and a pen or a pencil. I'll just give you a couple of seconds to do that because I know we didn't give you much time at the start before we kicked off. So we're going to go through each planet. We're going to talk about some different facts and some interesting things about each planet, and then we're going to use the information to start our diagram. So we'll start off with our very, very first planet, the closest planet to the sun, and that is Mercury. Now, Mercury is incredibly close to the sun, so it gets a lot of that incredibly hot heat energy from the sun, which you would think would make Mercury the hottest planet within our solar system, but it's actually not the case. Mercury is only the second hottest planet in our solar system, reaching a temperature of about 427 degrees, which is still incredibly hot. Perfect temperature if you're looking to make a wood oven pizza, but not a great temperature for living on. So certainly not a habitable planet. But the reason it is not the hottest planet, and that award falls to the next planet we'll talk about, Venus, but the reason it's not the hottest is because it doesn't have a very good atmosphere. Mercury is very, very poor at trapping heat. So while it's able to get incredibly hot on the side of the planet that is facing the sun, the side of the planet that's getting all that heat directly onto it, its dark side of the planet, so the planet that isn't facing the sun, which is not very, very good at trapping that heat, actually drops to very, very low temperatures, about minus 180 degrees. Now that gives Mercury a temperature range of 600 degrees Celsius, which is huge. By comparison, the maximum temperature ever recorded on the planet Earth was 56.7 degrees, and the minimum was minus 89. So Earth has a range of about 145 degrees Celsius. So Mercury has a range of 600, Earth's only got 145, and that's all because of the atmosphere. Now, Mercury being the closest planet to the sun, it also has the shortest year, the year being the amount of time it takes for a planet to orbit the sun fully. Mercury circles the sun every 88 days. So once every 3 months or so, Mercury is able to orbit the sun. Now we're going to start our diagram of the solar system. So take your A4 bit of paper and put it on a landscape view in front of you. So it's a long ways across. In the top left-hand corner, the very, very top left-hand corner, I would like you to put a very small S, because that S in the top left-hand corner is going to be your sun. That is where the solar system begins. The sun is at the center of our solar system. After you've got your S in the top left-hand corner, I'd like you to take your ruler, putting the 0 on your ruler on the S, and Mercury in our diagram is going to be 0.4 centimeters away from the sun. So take your ruler. I want you to measure your ruler on a diagonal. So your ruler should stretch from the top left-hand corner to the bottom right-hand corner. So on an angle away from that top left corner. Measure 0.4 centimeters or 4 millimeters away from the S and draw one dot. Mercury in our scale diagram is going to be one dot, and that dot is going to be, we're going to use that size of Mercury as a scale for the rest of our planets afterwards. So Mercury, starting from the S in the top left-hand corner, 0.4 centimeters away, and it's represented by just one dot. Okay, we'll move then on to our next planet, which is Venus. Now, Venus, like I said before, is the hottest planet in our solar system, maxing out at 462 degrees Celsius. So about 30 or so degrees hotter than we saw on Mercury. Now, the reason Venus is the hottest planet in our solar system is because of the greenhouse effect created by a very, very strong atmosphere. Now, Venus's atmosphere is about 100 times more massive than the atmosphere on Earth. Now, being more massive, being thicker and heavier, means it's much, much better at trapping heat. So heat gets to Venus from the sun, it hits Venus, and then once it's into that atmosphere, it cannot escape very well. So much more of the heat that reaches Venus actually stays there. If you're sort of thinking about, well, what's a translation is, as we're getting colder, you might find that you put a very, very thick blanket on your bed. And the reason you put a thicker blanket on your bed is because a thick blanket, being heavier or more massive, is better at trapping the heat from your body, and it keeps you warmer when you're trying to stay warm. When during the summer months, when you're already very warm, you might only put a very thin sheet, which would be a very poor atmosphere and would allow more of your body heat to escape. So the thickness of the atmosphere, the mass of the atmosphere, acts the same way as a blanket does. The more massive the atmosphere, the warmer the planet. And that is why Venus, with its such a massive atmosphere, is the hottest planet in our solar system at 462 degrees. It's also got another claim to fame in that it was the very first planet to be visited by a man-made object. In 1970, the USSR at the time actually sent spacecrafts to Venus. They were actually able to land it. And if you Google this later on, you'll actually be able to see photos taken from the spacecraft called Venera 13. So that's Venera, Venera 13. And they were able to take photos on Venus. So it's obviously a very dry and hot land, but it's cool to be able to see some photos from another planet. Moving back to your scale diagram now, take your ruler once again, starting it on the S, the same way you did before. So your 0 should be on the S. Now Venus is going to be 0.7 centimeters from the top left corner. And to show its size, Venus is about the size of 3 dots. So Mercury is 1 dot, Venus is 3 dots, 0.7 centimeters or 7 millimeters away from the S. So just draw that in, still on that diagonal, heading towards the bottom right-hand corner. So 7.7 centimeters away and 3 dots. Okay, moving along now to what I hope is everyone's favorite planet, which is going through a pretty tumultuous time right now, but that is the planet Earth. Now, from a space point of view, Earth is actually quite close to Venus, only 44 million kilometers away from Venus, but like I said before, it's obviously much, much cooler. We said the maximum temperature on Earth's never exceeded 60 degrees, while Venus is pulling out about 460 odd. So 400 degrees difference. Why is that? Why is Earth just so much cooler? The reason we're able to shield ourselves from those damaging solar winds that come from the sun and heat up planets so well is because the Earth is surrounded by a very, very powerful magnetic field. That magnetic field is there because the inside of Earth is made up of of molten iron. And molten iron, being a metal, has its magnetic properties, and it's able to give Earth a giant magnetic field, which is so strong it deflects the solar rays away. So lots of the heat from the sun that should be hitting Earth and should be heating us up is actually being deflected away. We've also got an atmosphere that's good without being amazing. It's certainly nowhere near as strong as Venus's, and so some of the heat is able to escape as well. So those are some of the reasons why Earth doesn't reach those crazy hot temperatures we've seen on Mercury and Venus. And really, without that magnetic field, it'd be too hot to sustain life as we know it. So Earth just wouldn't exist the way we see it now if it wasn't for that magnetic field and the atmosphere around it too. Now, moving on to your diagram, again, taking your ruler and putting it on the letter S, Earth is 1 centimeter away from the letter S in your top left-hand corner. So about 1 centimeter away should be the letter S, and its size is about 3 dots. So same size as Venus. Earth and Venus are very, very similar in size. Earth is just that little bit further away. So Venus was 0.7 centimeters or 7 millimeters. Earth is 1 centimeter away or 10 millimeters, but the same size is 3 dots. Moving along now, the planet Mars, probably one of the more interesting planets and one that's going to really shape science for for many years to come, I believe. Mars is that planet that NASA and the other space agencies, they've decided, well, this is where we're going to land next. Humans have set foot on the moon. We've done that. We've seen the moon. We know a lot about the moon. So the next thing for humans to conquer is Mars. Now, we've actually already launched 18 successful missions to Mars. And you can see that by things like the Mars Orbiter, which currently orbits Mars, and things like the Curiosity rover, which is a bit of a car type thing that's driving around Mars, taking photos and samples and whatnot. But we've also had 26 failed missions. So it wasn't easy to get there. Certainly reaching another planet is one of the most amazing feats of humankind, but we're pretty confident now that we can do it and we can do it well. So they want to take one more risk and actually send a manned mission to Mars. Now, take a second and just think off space for a minute. Can you tell me some names of some famous explorers? What famous explorers have you learnt about either at school or you've seen on TV? Have a think about that. What are some famous explorers you know of? Some names coming to mind, like people like Christopher Columbus or Captain Cook. But these were all happening hundreds of years ago, It's been a long time since we had a great explorer really come to light in humankind. Probably the last great explorer would have been Neil Armstrong. He was the first man to explore the moon. Where do you think that next great explorer is going to go then? If the moon was our last great exploration, where do you think the next great explorer is going to go? Is they're going to go to Mars. I think we're all going to be incredibly lucky in our lifetimes to be able to actually witness this take place. There's lots and lots of work going on into it. They've set timelines, they've set targets. I think we're all going to be able to enjoy that same moment that they had when humans first set foot on the moon, that kind of live broadcast where we all to witness humankind setting foot on Mars for the first time, which would just be an amazing thing to witness, I think. For a human being to set foot on another planet is, again, just a remarkable scientific feat. Now, going back to your diagram, Mars is about 1.5 centimeters from the S. So taking your ruler, measuring 1.5 centimeters from that S in your top left-hand corner, and its size, it's a bit smaller than Earth. It's about, we'll say it's 2 dots. So more accurate, it's probably one and a half dots, but it's going to be very hard to do that. So I would say Mars is 2 dots. So 1.5 centimeters away and 2 dots for Mars. Now, those planets we've talked about, Mercury, Venus, Earth, and Mars, those are what we call our terrestrial planets. These are planets made of, I guess, Earth-like subjects, solids, very, very solids. You technically could set foot on it if you could withstand the heat. Our next planet brings us to our first of our gas giants, and that is the largest planet in the solar system, and that is Jupiter. Now, Jupiter is by far the largest planet in the solar system. It is so large that all other planets could fit inside Jupiter. But it is just gas. It's lots and lots and lots and lots and lots of gas particles all being held together. With them so many together, they have their own gravitational pull because they're all bunched so close together. So while planets could literally go inside Jupiter because it is just a gas, and we could set foot in there. Well, you'd set foot through it, I suppose, more so. It also has uniquely the shortest day of all planets within the solar system. So a day on Earth is the time it takes for Earth to do one full rotation. Do you know what we call that? We would call that a day on Earth, which is 24 hours. So Jupiter is spinning twice the speed that Earth is. It's spinning, it does one full rotation every 9 hours and 56 minutes. So a much shorter day on Jupiter. It'd be very hard to get anything done the day on Jupiter with you always having to get sleep and whatnot. Not much time in the day at all. For our diagram, and this is where we start to see a really, really big distance now that we couldn't see on that earlier picture of the solar system. Jupiter is 5.2 centimeters away from your sun. So take your ruler in your top left-hand corner, and it's 5.2 centimeters away from the sun. Now, for dots, Jupiter, like I said, it's absolutely massive. Jupiter is 35 dots. So I need you to count it out. It's going to take some time. Jupiter is 5.2 centimeters away from the sun in the top corner, and it's 35 dots. I'm going to give you a few more seconds to do that because the 35 dots is going to be a lot to draw. Okay, moving along then to the next planet, and that is the second of our gas giants, a planet famous obviously for its rings, which are visible from Earth through a telescope, and that is Saturn. So like Jupiter, it's a gas giant made entirely of gas, but Saturn is actually less dense than Jupiter. So density is virtually the mass of an object in such a small space. So Saturn is less dense than Jupiter. It's actually has such a low density, it could actually float on water. So if we had a pool big enough, which obviously we don't because Saturn is massive and far, far bigger than Earth as well. If we did have a pool big enough, you could rest Saturn on top of it and it would float. Even its rings, the rings that are very, very clear from space, they're actually all just little specks of dust being held together by gravity as well. So while they are very visible and very easy to see, they're actually made up of billions and billions and trillions of very, very small bits of space dust. So yes, these very tiny little things combine to make something visible across the solar system, which is quite impressive. Now, on your diagram, once again, we see a big distance from Saturn. Saturn is 9.58 centimeters from the top left-hand corner of your page. Now, it's not quite as big as Jupiter, but it is still going to be 30 dots. So 9.58 centimeters from the top corner and about 30 dots. And once again, I'll give you a few seconds to be able to count out those 30 dots. Okay, moving along now to the planet, which is really hard to say without making everyone laugh and I do a live lecture. So this is one of the benefits, I suppose, of doing this. I can't actually get distracted by the audience, and that is the planet Uranus. Now, this is the first of our two ice giants, but Uranus actually is the coldest of any planet within our solar system. That is, once again, due to the atmosphere around it. Like we talked about with Mercury, is not very good at trapping heat. Uranus is the same. It doesn't receive much heat from the sun, but the little heat that it does receive, it doesn't trap well at all. So it's a very, very cold temperature of minus 220 degrees. Now, because it is so cold, it gets the term of an ice giant. So that's what we call it. We have our two gas giants in Jupiter and Saturn, and now we have our ice giant as well. It's not ice the way we know it. It's not a big ball of ice you could put into an even bigger, glass of Coke when you are hot. It's not water, iced water like we know it, but it is other chemicals that at these low temperatures do freeze up, and so we call it an ice giant. Now, when you're drawing Uranus, it is very, very far now, 19.14 centimeters away from the sun. So take your ruler, drawing it up starting at the S, its size is 13 dots. So 19.1 centimeters away from the sun in your top left-hand corner, and its size is 13 dots. So less than half the size of Saturn, but still much, much bigger than Earth and the other terrestrial planets we learned about earlier on. So final one last time, 19.1 centimeters from the top corner, and the size is 13 dots. So moving along now to the final planet in the solar system, the 8th planet from the sun, and that is Neptune. Now, like its closest neighbor Uranus, it's also considered an ice giant, a very, very cold planet, not really receiving much heat energy at all from the sun due to the great distance between the two of them. But I guess its most interesting characteristic is that it has the longest year. We know that a year is the amount of time it takes for a planet to orbit the sun. And so for Neptune, that is 165 Earth years it takes for Neptune to complete one orbit. So in the time it takes Earth to rotate once, which we know is 365 days, it takes Neptune 165 times that. So a very, very long time. Throughout that journey, Neptune travels over 1 trillion kilometers, which is just an outstanding distance to travel. Now, to finish off your diagram now, you're going to draw Neptune. So take the ruler in the top left-hand corner, and Neptune is going to be the full 30 centimeters from the sun in the top left-hand corner. So 30 centimeters away, and its size will be 13 dots. So a full 30 centimeters away, and its size is 13 dots. And that concludes our solar system. So what you have in front of you now is a scale diagram of the solar system. And one of the extension activities you might want to do later on to earn some more time in your passport is actually make that a lot bigger. You've got a scale diagram now on an A4 bit of paper, but can you make that grow? Could you go and do it on a footpath where instead of it being 1 centimeter, it becomes 1 step? And so, for example, Neptune is now 30 steps away. Could you do it on your fridge? Could you do it along a tall tree, something like that? So we're looking for the most creative ways and places our students can create some scale diagrams of the solar system. Now, it's usually this point in the lecture when I do deliver it publicly and in person that I start to notice people getting a little bit shifty. We have, often the adults as well will start looking a little bit concerned, looking to one another, kind of looking a little bit at me, and hands start to go up, and people start to ask the question, well, what about Pluto? You've just talked about the solar system, you've gotten to Neptune, and you've stopped. Why aren't we including Pluto as a planet within the solar system? And it's simply because Pluto is no longer considered a planet. Even when I was in school, I completely agree, we were taught that there were 9 planets in the solar system. But in 2006, the International Astronomical Union reclassified Pluto as a dwarf planet. And so it was no longer included as a planet in the solar system. Now, classifying things is a really key part of science. It's all scientists, no matter what field they work in, they like to classify objects, whether that be as an organism versus a microorganism. We like to classify, right now you're hearing a lot about a virus versus a bacteria, for example. So scientists really like to classify. And they set certain rules to guide that classification. So it's no different with planets. For something to be classified as a planet, it has to meet 3 key criteria. And I want to run through those so we get an understanding of why Pluto was removed from that list. The first thing a body must do to be considered a planet is it must orbit a star. It must complete 1 full rotation around a star, and Pluto does that. it does. It takes longer than Neptune, but it does complete one full rotation of our sun. So check, 1 from 1, we're all good so far. The second thing a body must do to be considered a planet is it must be spherical in shape. You will have noticed as we looked at the pictures of the planets throughout this lecture that they all carry the same shape. They're all roughly a sphere. They may not be perfect spheres, and that's a little bit different for each planet, but they're looking to be as close as they can to being a sphere. And that's because that's the shape that gravity forces them into. A sphere is the shape that allows every little bit of mass to be as close to its center of gravity as possible. And so that's why it's a sphere. You don't see planets as pyramids or as cubes. You only see planets as spheres. And Pluto is that as well. Pluto is quite close to being a perfect sphere. So far, 2 from 2. It's the third criteria where Pluto loses its classification as a planet. It is very important for a planet to what it's described as dominate its surrounding area. So that means a planet's gravitational pull must be so strong that it sweeps up any sorts of asteroids, comets, or any other space debris as a part of the orbit. Think of it like a vacuum cleaner that as it goes along, it must suck up everything around it because its gravitational pull is so strong. Other planets do that very well. It is one thing Pluto does not do. It just does not have the strong gravitational pull. Think of it like a really poor vacuum cleaner. It's not picking up much at all. It's going along, it's still moving through space, but it's not picking up much. It's just not strong enough. It's a vacuum cleaner, the motor's starting to wear down. It doesn't have the strength in it. Pluto's the same. Its gravitational pull is just not strong enough to be considered a planet. And that's why it got removed. Now, it is an odd thing to do. People often question, well, why bother? Why not just leave it there? Why change it? And I think what's interesting to learn is that if we had that policy, if scientists allowed Pluto to be classified as a planet, it wouldn't just mean there were 9 planets in the solar system. We would then have to count about 44 other dwarf planets, which are in our solar system, as planets as well. So Pluto is actually one of many, many dwarf planets that just don't get considered as one of the 8 planets in the solar system. And that's why scientists made that decision. It is still up for debate, though. It may well change again within our time. Now, the very last slide I want to talk about today is this in here in front of you. We call the idea of a Goldilocks planet. So one of the biggest questions, I suppose, in all of science, not just in astronomy, is that, well, is there life out there? Right now, humans have only really found life on one planet, and that is the planet Earth. From a scientific point of view, given there are just so many planets out there in so many galaxies and solar systems throughout the entire universe, like we talked about earlier on, we are just a very minor part of it. There's a pretty good chance there is life somewhere. And scientists really want to find that life. So what they do is they look for planets within what we describe as the habitable zone or the Goldilocks zone. That is a zone that is close enough to the planet that it's warm enough, but not so far away, so close that it's too hot to sustain life as we know it. And for human beings, we look for, do we think there could be liquid water on there? We know that liquid water is essential for life. So we are looking for planets throughout the galaxy that we believe are close enough to a star to receive enough energy for that planet to sustain liquid water. And now it's an area of science that is going to continue on for a very, very long time. And I think there's definitely a good chance that some of you who are listening today, you could also have the opportunity to be involved in answering probably one of the biggest questions for all of humanity. And with that concludes the lecture, everyone. I wanted to thank you very much for taking the time to join me today. Really sorry about the delay, and I hope those of you that now who are able to listen to this as a recording were still able to take a lot from it, and I was able to teach you a thing or two. The diagram that you have created in front of you, that will act as your evidence, and that can either be uploaded to the Children's University portal or shown to your in-school coordinator as evidence. There will be some extension activities posted to both the portal and the website in follow-up of this that you can also do to earn more hours in your passport. But for those of you with an interest, like I said at the start, I've come into this with just an interest in space and that sort of thing. So there are plenty of great documentaries and books and things out there that you might want to watch to educate yourself and really, really peak that knowledge that you're going to have into what's a really, really exciting field. So stay safe, enjoy your holidays, and we hope to hear from you again soon at Children's University. Thank you.